Bio 245. So, still Vanessa. Hi. This is going to be part 2 of our sliding filament theory series of videos. So, this should be the last part. I'm sure you guys are happy. But in the last video, we talked about muscle as a whole, what it's made up of and its constituents. We talked about muscle fibers or muscle cells and how it's made up of those myofibrils, which are those compacted proteins all kind of shoved together, and how those myofibrils, if you were to break them open and just look at them, that those myofibrils are made up of individual protein strands, complex protein strands, and that we have thin filaments and we have thick filaments, and that they look red or they look clear. So now we know what we're looking at when we're looking in the microscope, and we know a little bit about how the muscle is composed. So how do these parts matter? How do they interact? Well, first off, let's talk a little bit about what the individual thick and thin filaments are made up of. So this is important. This has everything to do with contraction. First off, for our thin filament, we actually have 3 proteins making them up. I know I said that they're thin and light shines right through them, but they are the most complex part of this as far as number of proteins. First off, we have this protein called actin. Actin you've probably heard about in the past. Actin, you can put a bunch of it together to stack it in really long strands, but in the case of a muscle fiber, the main constituent of our thin filament is going to be actin. So here's just another drawing of our thick and thin filaments. Those black lines, the majority of that is going to be actin. Actin is made up of these individual ball-like structures. I think you can see that, excellent. It's made up of these individual ball-like structures, and each of them has a binding site, and we'll talk about why those binding sites are important, but I've indicated them with green dots. The other really important protein that you're going to find on thin filaments is called troponin. Troponin. Troponin is what's referred to as a regulatory protein. So if you see a question on practical or on a quiz or whatever that says which protein of the thin filament is the regulatory protein, that's troponin. The reason why it's referred to as a regulatory protein is because it's controlling whether or not that binding site I was talking about a couple seconds ago on actin, it's determining whether or not that binding site is blocked or not. Okay? So there's a binding site there, but sometimes it's obscured and sometimes it's not. Troponin decides that. How does troponin decide that? Well, you might notice that I drew that troponin a little bit like a Pac-Man. So he has like an open mouth waiting for something to come into it. In this case, what it's waiting for is calcium. This should be bringing back memories from when we talked about excitation-contraction coupling. You remember that the super important event to happen is that that neuron talks to the muscle cell, and that muscle cell becomes excited, and it releases all that calcium. And I mentioned at the time in that video, I was like, calcium's a big deal. That is what allows contraction to occur. Here we go. Now that calcium's coming into play, right? So we have troponin here, and he has a binding site open to calcium. So calcium I've represented again, whoops, wrong color. I've represented once again as this kind of baby blue circle, just so you know, that's what that is. Anyway, so it has this open binding site for calcium. When calcium comes into that binding site, troponin will physically change shape. I've represented this change in shape as simply just laying on its side. So it goes from standing up, waiting for calcium, to going like this. Okay, so there you go. There's open troponin, there's troponin with calcium bound, and it is twisted over. So that's its conformational change. This is how it regulates whether or not that binding site is covered. So what is that binding site normally covered with? Why is it covered at all? Well, it's covered with this other protein referred to as tropomyosin. Remember, I told you we're going to see myo a lot, and myo always means something about muscle, right? So we've got tropomyosin. Tropomyosin, its job is it acts like a little rope. It's a little rope that wraps around the entire thin filament. So here's our actin. If we have and I have it drawn completed down here, but I just want to show you what I'm talking about. So if we have our tropomyosin, it actually physically wraps around like that, like a little rope, right, just like that, like a helix. It just twists around the entire thin filament and covers those binding sites. So that's why we need troponin. There's our little happy troponin living his life, okay? So he's sitting there, and he actually, if you want to imagine how troponin and tropomyosin interact, troponin kind of holds the tropomyosin. Like I mentioned that the tropomyosin is like a rope. It holds it like a little rope. And when it binds that calcium, it lays over and twists over. It's holding that rope of tropomyosin, and it takes it with it. It goes, yep, we're moving out of the way, so we can allow that binding site to be cleared. So what happens then, I don't want to draw it again, but basically we have our, well, I kind of have drawn here, but anyway. So we have our troponin. It's going to bind onto calcium, right? So it's going to lay over like so. It's going to bind onto calcium. Life is good. And it's going to physically move that rope with it, so it's no longer blocking the binding site. So here's our little binding site in green. It is now exposed because that troponin has bound with the calcium, changed conformation, and it's twisted that rope right along with it. So this is our non-bound troponin and tropomyosin. Here is our bound. Okay. And the way you should think about this a little bit, at least, if you guys know about proteins and how they're composed, you know that they're built out of amino acids. Those amino acids have various charges. Whenever you introduce a calcium ion has 2 positive charges on it. Okay, 2 positive charges. So when it adds that 2 positive charges into the mix, it physically changes how that protein is shaped. All those amino acids that have all these various charges, they fold together because of how the positives and negatives interact. If you add in a super high charged positive into the mix, it physically makes the protein change conformation. So in other words, this isn't something that requires energy, it's just something that changes the way that the protein conforms as far as its shape. Okay? The reason why I mention this is because we do need energy for this other interaction to occur. Alright, so this little picture I drew right here represents the thin filament as a whole. So we have our little blue troponins with little open mouths waiting for calcium. We have our pink tropomyosin blocking those binding sites. And we have our actin with the green binding sites, and those are covered. So that's what makes the entire thin filament. For the thick filament, it's more simple. There's only one protein to worry about. The protein, if you just dissociate it and look at it by itself, we have these red golf clubs that are twisted together. So here's the golf club heads, and then there's the handles, and they're all twisted up. So whenever you see myosin is the one protein that makes up our thick filament. But whenever you see myosin by itself, this is what it's going to look like. Okay? So if we kind of put it in the context of our thick filament, here we go. We have all the little handles that are twisted together, and then there's all the little golf club heads sticking out. You'll notice that each of these individual golf club heads, I have either an ATP docked or I have an ADP docked. So remember how I told you that with troponin, that's a conformational change, so it doesn't require energy, it just requires charge. So that charge introduced to the protein changes its shape, so it changes conformation. In the case of this guy here, he changes conformation, but it's like a tight spring action. So it's not something that just is like and moving over. It's something that, like, we'll describe it in a second, but that ATP needs to be bound onto the myosin in order for it to do its job. It'll physically grab onto that thin filament and yank it really hard. So you need more energy than just a conformational change will supply. That's why we need ATP. So we got ATP docked into myosin, and after myosin's done its job, or as it's doing its job, it releases one of those inorganic phosphates to form ADP. So you guys should know that when we have ATP and ADP, what I'm talking about is we have an adenosine, right? And it's got 3 little P's, just to recap in case you don't remember. So ATP is tri, that's 3, so 1, 2, 3. And if you have ATP, we have these phosphates that are tightly coiled together. When you want to release that energy, you pop off one of those P's on the end. That relaxes the bond. So it actually releases a bunch of energy when that spring is sprung, so to speak. So we have either ATP on board, that myosin head's ready to go and wants to grab onto that thin filament, or we have that phosphate's been popped off, so now that myosin head has done its job, it's tugged really hard, and now it just has ADP. So that's the form where it's done its job and it is now relaxed. Okay. So how does this all kind of work together? Why am I talking all about this? Oh, the other thing I want to mention real quick. You'll notice I have this on the end of our myosin heads in green. That might look a little familiar from our actin binding sites, which are also green. Okay. Okay, so here's how everything's arranged. I already mentioned to you that our thick filaments are kind of here, and our thin filaments overlap them. So if you want to think about how they're relating to each other, they're interlinked like this. So they're not completely interlinked like this, they're overlapping slightly, okay? So here's our thick filament, so to speak, so that it makes a little bit more sense with the drawing. Here's our thick filament with our myosin head sticking out, and you can see that they're right almost against our thin filament. Our thin filament has our actin, right? And it has our tropomyosin covering that binding site, and here's our troponin with its waiting mouth, waiting for calcium to come in. Okay? Now, the big deal about this here, these green spots, myosin wants to touch the binding site for actin. So the green wants to glom on to the green, but can't, because that tropomyosin's blocking the way. What a jerk, right? All they want to do is be together so that they can have a reaction, so life is great, but that tropomyosin's just blocking things. It's total drag. So how do we get it to move out of the way so it's no longer blocking it? Well, that's where our excitation-contraction coupling comes in. So we have our thought. We send a message down to that neuron. That neuron becomes excited and it sends out some neurotransmitters onto that muscle fiber. The acetylcholine binds onto the motor end plate. Then we have an excitation of that muscle cell. Then we have release of calcium from the endoplasmic reticulum. Right there, like that, okay? So the next thing that happens is here. We can see that our little troponin guys with their little open waiting mouths have caught that calcium, okay? So now they're happy, they've glommed onto that calcium. And you can see that they've all changed conformation, so they're all physically twisted over now. And you can see that as a result, that tropomyosin's kind of tilted out of the way. So here's our tropomyosin rope, and it's been physically moved out of the way by our troponin changing conformation. This reveals our binding site. So you can see that the green is completely exposed. And right away, just like a magnet, that myosin head goes glomp right onto it. So you can see that as soon as it's exposed, the myosin heads glom on, okay? You'll also notice that we had ATP on board before. So in other words, the myosin head's ready to go. It's got that stored energy. It's like, yeah, we're ready to do this. So as soon as that binding site is exposed, it gloms on like a magnet, and it quickly hydrolyzes that ATP. So it goes from that tight, coiled up phosphate form to popping off that phosphate, releasing that energy, and we get a really strong tug of that thin filament, which I've indicated with this arrow here. So it's actually physically dragging the entire thin filament over. And I have that represented up here. So just to orient you once more, we have our Z-line, which is that supporting scaffold structure for our thin filaments. And we have our thick filaments as well. You can see in this top one here that they're just barely overlapping like so. Okay? So this is the form where we have no calcium present. So we're relaxed, the muscle is long. Okay? Then we release calcium, and life changes drastically in this cell. Okay? So we release calcium, then that troponin binds onto the calcium, moves that tropomyosin out of the way, exposing that binding site, and basically imagine tons and tons and tons of these little myosin heads like that. Tons and tons and tons. They like wrap all the way around. There's a million of them. So you can imagine that all of these guys suddenly have a binding site to glom onto. So they all glom on and they all tug and tug and tug. So it goes from these long sarcomeres to physically dragging those Z lines together. So they become, the sarcomere itself becomes physically shorter. Okay? So this Z line and this Z line has moved in towards each other because these guys are tugging on those thin filaments and physically pulling on it. Okay? So that's basically what's happening. I can't physically show that on the board, but there's a really awesome video link that we have in your PowerPoint for you to check out, and it will physically even show that myosin head dragging on that. I don't know, I wish I had a rope or something, but here, Anna, give me your hand. So if she's actin and I'm myosin, her binding site becomes exposed, I grab and I pull, and I grab again and pull, and I pull and pull and pull and pull and pull until we're practically hugging each other and we're great friends and life is great, right? So that's physically what's happening. Just to recap, I know I've recapped a million times, but I want it to be clear. We have our thin filaments and we have our thick filaments. Remember, they're called myofilaments. just as a general broad category. Our thin filaments are made up of 3 proteins: actin, troponin, and tropomyosin. Actin has a binding site on it, troponin can bind calcium and change conformation, and tropomyosin is basically like a little rope that wraps around our thin filament. Normally, in our normal composition, we have tropomyosin covering our binding sites, and troponin holds that tropomyosin like a little rope. And then we also have our thick filament, and our thick filament is made up of a protein called myosin, which looks like 2 golf clubs twisted together. If you get tons and tons and tons and tons of them together, you get a thick filament with all these little myosin heads sticking out. And it sticks out all over. You'll see that in some of the pictures, the way that it's depicted. So, what happens then is you can have, here's your situation where you have your thin filaments and your thick filaments overlapping. You release calcium into the system. Troponin binds onto that calcium, moves that troponin out of the way, exposing that binding site. Now our myosin heads can do their job, glom onto that binding site, which results in a chemical reaction inside of the myosin head, which releases that phosphate, and then that guy can physically pull onto our actin strand. And if you zoom out, here it is relaxed with no calcium present, and here it is with calcium present, and the sarcomeres have contracted. And so when we contract our sarcomeres, again, we shorten our myofibril, which is that packed tube of proteins. We shorten the entire muscle cell, we shorten the fascicle, and we shorten the whole muscle so it can act as a pulley and perform contraction. So that's the end of part 2 of our sliding filament theory stuff. Definitely check out the next video, which is going to be the muscle fiber model, so that way you guys know how to identify stuff. And if you haven't seen part 1 or you haven't seen the excitation contraction coupling video, definitely check those out. It'll make this make more sense.